Hello, this video is for Algebra 1. It is Chapter 2, Lesson 7. The title of the lesson is Rates, Ratios, and Proportions. The objectives for this lesson are to write and use ratios, rates, and unit rates, and also write and solve proportions. The vocabulary for this lesson, and it is rather extensive this time, is ratio, rate, scale, unit rate, conversion factor, proportion, cross products, scale drawing, scale model, and dimensional analysis. So why learn this? Well, ratios and proportions are used to draw accurate maps, and we'll see an example of that in example 5. So a ratio is a comparison of two quantities by division. The ratio of A to B can be written A colon B, or it can be written as a fraction, A over B, where B is not equal to 0. Remember that every fraction is a division problem, so A over B is one way that we can represent a ratio. Ratios that name the same comparison are said to be equivalent. A statement that two ratios are equivalent, such as 1 over 12 is equal to 2 over 24, is called a proportion. Note that if we divided 1 by 12, we would get the same result of dividing 2 by 24. I know this because, well, to get from 1 to 2, we would multiply by 2, and then if you multiply 12 by 2 as well, you would get 24, so I know that these two ratios are proportionate to one another. You could also use cross products, and we'll get into that a little later, but real quick, notice that 1 times 24 is equal to 12 times 2. That's cross products, and we'll look at solving proportions using cross products later on in this lesson. Looking at our next slide, we have example 1 using ratios. Now let's look at our reading math real quick off to the side here. Read the proportion 1 over 15 equals x over 675. Well, whenever we're dealing with proportions, we would do this a little bit differently. We would read it as 1 is to 15 as x is to 675. Notice the difference is at the fraction bar and the equal sign. Instead of saying equals, we would say is. And for the fraction bar, instead of saying 1 over 15, we would say 1 is to 15. So 1, and the fraction bar is 2, and then state the number 15. The equal sign as, again, x, again the fraction bar is 2, and then our denominator 675. 1 is to 15 as x is to 675. So using ratios, the ratio of faculty members to students at a college is 1 to 15. There are 675 students. How many faculty members are there? Well, part of the issue here is knowing how to set it up. Well, notice that they say faculty members before students, and here's the word to right there. So we could think of this as faculty members is listed first, students is second. So faculty members will be our numerator, and students is going to be the denominator. Whatever category or measurement that they give you first is going to be your numerator. And then following the word to, they're going to give you the second category or measurement. In this case, it's students, and that's always going to be your denominator. So first we want to write a ratio comparing faculty to students. So faculty numerator, students denominator. Now let's plug in our number of faculty members, 1, to our number of students, 15. Then we can write a proportion, and we're going to let x be the number of faculty members because that's the unknown. It says how many faculty members are there. So number of faculty members is the unknown portion, and we're going to use an x to represent that unknown value. So 1 is to 15 as x is to 675. So since x is divided by 675 over here on the left, we're going to multiply both sides of the equation by that denominator, 675, and then the 675 is going to cancel each other on the left, leaving us with just x. Then 675 times 1 is 675. Divide that by 15, we would get 45. So therefore, there are 45 faculty members for those 675 75 students. So let's look at the check it out here. The ratio of games won to the games lost for a baseball team is 3-2. So let's go ahead and what's the numerator going to be? Well, the first thing they mention is games won. So we're going to take the games won and we're going to make that the numerator. And then they mention games lost, and notice the word 2 right here. So 1, 2, lost. So 1, 2, lost. Now let's go ahead and take the ratio they give us. 3-2, 3 won, 2 lost. And now it says the team won 18 games. How many did the team lose? So losing is the unknown. So it's the X value is going to be down here, the unknown value of, or the unknown number of losses. But we do know that they won 18 games at this point here. So in that case, let's go ahead and I'm going to move this over a little bit so that we have it separated from that. Give us a little bit of room to work. Now, I would prefer to go ahead and solve this using cross products. However, we're pretending that we don't know about cross products yet. So we'll probably do this just a little bit different. And I'm going to go ahead and move this up just a little bit more so I got some more space. So let's go ahead and get the X out of that denominator position. Let's go ahead and multiply both sides by X. And whenever we do that, these X's will cancel here. X times 3 is going to be 3X over 2. And then equals, and when we still have the 18 on the right. Now I want to multiply both sides by 2 to get rid of that denominator. Multiply by 2. The 2's will cancel each other, leaving me with 3x on the left. And 18 times 2 is, what is that, 36. Now let's go ahead and divide by 3. Believe me, using cross products would have been a lot easier on this one. The 3's will cancel each other, leaving us with x, and 36 divided by 3, what is that, 12? So in this case, the team lost 12 games. All right. You're going to see later on, cross products would have been a lot easier. Whenever we get to that, you'll see, wow, should have used cross products. All right. Moving along, a rate is a ratio of two quantities with different units, such as 34 miles to 2 gallons. Notice that the numerator is in miles, and the denominator is in gallons. We're comparing miles to gallons, so this is a rate. Whenever we talk about rate of speed, we're talking about miles per hour. So if we were talking about rate of speed, we would have miles per hour. And this division bar here, often we pronounce that as per. So miles per hour. That would also be a rate, your rate of speed, right? So rates are usually written as unit rates. A unit rate is a rate with a second quantity of 1 unit, such as 17 miles is to 1 gallon, or 17 miles per gallon. And you'll also notice that 17 miles per 1 gallon is the same as 34 miles per 2 gallons. We just divide both the numerator and the denominator by 2, and we would get down to 17 miles over 1 gallon. But the point is here that we know that this is a unit rate because the measurement in the denominator has a value of 1. So instead of knowing how many miles can we get for 2 gallons, we want to know what can we get for 1 gallon, and that would be 17 miles. So 17 miles per 1 gallon is a unit rate. We know this because the denominator has a value of 1. You can convert any rate to a unit rate. So in example 2, finding unit rates, and I'm probably going to crucify this poor boy's name. So Takeru Kobayashi of Japan ate 53.5 hot dogs in 12 minutes to win a contest. Find the unit rate in hot dogs per minute. So notice the word per right here. So we know this is where our fraction bar is going to be. So it's going to be hot dogs over minutes. So 53, and we'll do H for hot dogs and M for minutes. So this is hot dogs per minute, 53.5 hot dogs per 12 minutes. Now we want to know how many did he eat in just 1 minute. So now our denominator here is 1, so we know that's important. So now, and again, this would be through cross products, but let's go this way. To get from 12 to 1, I would have to divide by 12. So to get to this value of x, I would have to divide the 53.5 by 12 as well. So you're going to find out that whenever you do unit rates, if you divide the numerator by the denominator, it's going to give you the value of what your new numerator is going to be, and the new denominator is always going to be 1, so it's going to turn into a unit rate. So with that said, 53.5 divided by 12 is approximately 4.46. Note here they ask us to round to the nearest hundredth. So the unit rate is approximately 4.46 hot dogs per minute. Let's look at the check it out. Corey earns $52.50 in 7 hours. Find the unit rate in dollars per hour. So it's dollars per hour. So we're going to have dollars per hour. So let's fill in our numbers. 52.5 over 7. And we want to get to where our denominator is 1. We would divide 7 by 7, divide it by 7 to get to 1. So we're also going to divide the numerator by 7 as well. And whenever we do that, hold on, need my calculator. And I'm going to go ahead and divide that 52.5, divide that by 7, and I will get 7.5. So that is 7.5. So this means that Corey earned $7.50 or $7.50 for every 1 hour. So the unit rate for dollars per hour is $7.50 per hour. Moving along, we'll look at the next page here. And now we're going to talk about dimensional analysis. Dimensional analysis is a process that uses rates. Remember, a rate is a ratio, and the numerator and the denominator are different measurements. So dimensional analysis is a process that uses rates to convert measurements from one unit to another. An example of a they're getting the conversion factor here. This is a conversion factor. I'm wanting to say it's a conversion factor, but they don't say that until here. So a rate such as 12 inches is to 1 foot, in which the two quantities are equal but use different units, is called a conversion factor. There you go. So to convert from one set of units to another, we need to multiply by a conversion factor. So let's back up just a minute here, talk about conversion factors. Note that 12 inches is equal to 1 foot, but the numerator is in inches and the denominator is in feet. So in this case, and I'm sitting here thinking, gee, this is also, but it's not a unit rate in this case because they're equivalent to one another. So we won't go there. I'm sitting there thinking the denominator is 1, but don't be fooled there. So other examples of a conversion factor would be, let's see, if we had 1 gallon is equal to 4 quarts. So this would be a conversion factor as well, because 1 gallon is equal to 4 quarts, but the numerator is in gallons and the denominator is in quarts. So that would be another example of a conversion factor. So moving along here, let's look at our helpful hint. In example 3a, step 1, pints appears to divide out, leaving quarts as the unit. Use this strategy of dividing out units when using dimensional analysis. And so we'll talk about what that is. So 3a, a large adult male has about 12 pints of blood. Use dimensional analysis to convert this quantity to gallons. Step 1 is to convert pints to quarts. So we have our 12 pints. Then we're going to use a conversion factor. 1 quart is equal to 2 pints. There are 2 pints in a quart, so these two are equal to one another. Numerator is quarts, denominator is pints. And we want the pints on the bottom because we want these to cancel out. And I'll do an example in a little bit that'll show that canceling out a little bit better. I think the textbook could represent it just a little bit better, and so I think I'll go ahead and do that in a moment. And so the pints cancel out. 2 times 12, or 12 times 1 is 12, divided by 2 is 6, so it'd be 6 quarts. So 12 pints is 6 quarts, but they want it in gallons, so now we need to convert quarts to gallons. So let's take our 6 quarts, multiply it times another conversion factor where we have 1 gallon is 4 quarts. Interesting, same conversion factor I used as an example up here. The quarts cancel each other out. 6 times 1 is 6. And then divided by 4 equals 1.5. So we would get 1.5 gallons. So a large adult male has about 1.5 gallons of blood. How I would have done this in working it out, if I need to go from 12 pints, let's go 12 pints. And I'm going to write this as a fraction because that way you can see the whole canceling out thing. This helpful hint about dividing out units. It's going to be a little bit easier to see if we represent the first measurement of 12 pints as a fraction of 12 pints over 1. Now, I need to get to gallons, right? So if I want to get to gallons, and I'm going to use the same conversion factors they did, let's get first to quarts. So in a pint, I guess I could put PT for pints. That would be better. And then QT for quarts, right? In 1 quart, there are 2 pints. And then let's get to gallons. And I'll show you why I set this up. Notice I'm putting quarts in the denominator, and I'm putting gallons in the numerator. And 1 gallon, there are 4 quarts. So as long as I keep situating my measurements to where I have one of them in the numerator and the other in the denominator, then they're going to cancel each other out. And here's what I mean by that. Notice that pints is in the numerator and pints is in the denominator, so I can cancel those two out. Quarts in the numerator, quarts in the denominator, so I can cancel those two out. Now I'm just left with my number values, and actually let's look at the measurements. Look across the numerators. What do we have left? We still have gallons, right? And we look across the bottom, and in this case, we're just going to have everything cancels out, so we're just going to have a number here, and which is good because they don't want a rate. They just want a number of gallons, and gallons is what we have left. So 12 times 1 times 1 is 12, and 1 times 2 times 4 is going to be 8, and then 12 divided by 8, 8 will go into 12 once with a remainder of 4, and our denominator still 8, and that 4/8 is going to simplify to 1/2, and we would come up with the same 1/2 that they have here. So the reason I did this here is so that you can understand that whole canceling out thing. And plus, you can use more than one conversion factor in a string of conversion factors. You don't necessarily have to do one. You don't have to do pints to get to quarts and then quarts to get to gallons in a separate problem. You could string them all together in the same line there. So let's look at the dwarf seahorse, and I'm going to probably crucify the scientific name here. I think I can deal with the hippocampus. However, it's the zostera. I guess that's zostera. Hippocampus zostera. Swims at a rate of 52.68 feet per hour. Use dimensional analysis to convert this speed to inches per minute. So we want to get to inches per minute. That's our target. Right now we have feet per hour, so we're at feet per hour. So we're going to need some conversion factors. We're going from feet to inches. Notice over on the left we have feet, on the right we have inches, on the left we have hours, and on the right we have minutes. So we're going to have 2 conversion factors, one to deal with distance and another one to deal with time. So use the conversion factor of 12 inches to 1 foot. So there's our conversion factor for distance to convert feet to inches. And use the conversion factor 1 hour is to 60 minutes to convert the hours to minutes. So there's our conversion factor for time. Now let's start filling things in. We have our first rate of 52.68 feet per hour. So we start off with that. Put in our conversion factor for distance. 12 inches is to 1 foot. Put in our conversion factor for time. 1 hour is to 60 minutes. And notice that feet is in the numerator. So whenever we set up our first conversion factor, we're going to put feet in the denominator because we want those to cancel. And then whenever we did our conversion factor for time, notice that hours is in the denominator. So we put hours in place of the numerator because we want these hours to cancel each other as well. They put them in colors. I like to cancel them out. So feet cancels feet. Hours cancels hours. We're left with inches and minutes. And notice that's what we have, inches and minutes. So everything seems to be set up quite nicely. Now we do our multiplication of all of our numbers, 52.68 times 12. And that doesn't equal 10. There's a little bit of something going on there. Let's see what that is. I'll show you what that is. So if we do the 52.68, and I'm going to multiply that times 12, That's going to give us 632.16. Now we're going to do 1 times 1 times 60 is going to equal 60. Now if we get to a unit rate, just 1 minute, because this is 60 minutes, we want to get to just 1 minute. So we're going to take that 632.16, we're going to divide that by 60 to get a unit rate, and then we get 10.536, and since it is a unit rate, it's going to be 1, and that was indeed inches, and the denominator is going to be minutes. So we get the inches per minutes. Now, check that the answer is reasonable. The answer is about 10 inches per minute. Well, there are 60 minutes in 1 hour, so 10 inches per 1 minute is 60 times 10, which is going to be 600 inches per hour. And there are 12 inches in 1 foot, so 600 inches an hour is 600 over 12, which is 50 feet per hour. So this is close to the rate given in the problem of 52.68 feet per hour. All right, let's move along to the next page. Here we are at proportions, and using proportions and cross products property, this is the bread and butter of it. If you want to solve proportions, cross products is the way to go. So in the proportion A is to B as C is to D, the products A and D and B and C are called cross products. You can solve a proportion for a missing value by using the cross products property. So in words, we say in a proportion, cross products are equal. So the reason they call them cross products, first of all, we're multiplying. Whenever you multiply two numbers, you get a product. And notice this little 2 times 6 and 3 times 4. Notice the red and blue lines here. They look like what? A cross, right? Or an X there. So we call them cross products. So 2 times 6, numerator of the first, times the denominator of the second on the left, and 3 times 4, the denominator of the first and the numerator of the second. We're going to put that on the right. 2 times 6 is 12. 3 times 4 is 12. So we know that 2/3 is indeed equal to 4/6. So in algebra, we say if A is to B as C is to D, and B is not equal to 0, and D is not equal to 0 because neither of these numerators can be 0, then the product of A times D is going to equal the product of B times C. Now, I often call the 2 and the 6 are the extremes, and the 3 and the 4 are the means. And here's the reason for that. If I set this up as a proportion or a ratio using a colon, that would be 2 is to 3 as, and then 4 is to 6. 4 is to 6. Well, notice that right here close to the middle, and whenever we talk about the middle, we talk about the means, right? Means is what's in the middle. So 3 and 4 are the means. Now, out here on the further edges, and whenever something's out on the edges, way out there, right, we call those the extremes. So these are the extremes. And notice that I'm multiplying the 2 times 6 first, so I have my extremes first. And then I set those equal to the product of my means. So you'll hear me say quite often, multiply the extremes, put those on the left, multiply the means, put those on the right. So whenever I talk about the extremes, I'm talking about the first numerator and second denominator. And whenever I'm talking about the means, I'm talking about the first denominator and the second numerator. So solving proportions, solve each proportion. So let's multiply our extremes. 5 times W is 5W, and 9 times 3, the product of our means, is 9 times 3. We end up with 5W on the left. 9 times 3 is 27. Let's divide both sides by 5 right here, and we're going to get 27 over 5. A lot easier that way, right? Now on the second one, we have an expression as our denominator, but that's fine. Let's go ahead and multiply our extremes. 8 times 12, that's on the left, and then multiply our means, the quantity of x plus 10 times 1. So that's on the right. 8 times 12 is 96. 1 times x plus 10 is just going to be x plus 10. Now let's subtract 10 from each side, and we get x equals 86. We'll do one example down here. Let's go ahead and I guess we'll do 4b. It looks like the tougher one. So we have g plus 3 over 5 equals 7 over 4. So let's go ahead and multiply our extremes. G plus 3, and we're going to multiply that times 4. And 5 times 7 is 35. Let's go ahead and distribute the 4 into the quantity of g plus 3. We would get 4g plus 12 equals 35. Looks like we're down to a two-step equation. Let's go ahead and subtract 12 from each side. So 35, 25, 23, right? Now let's divide both sides by 4. 23 divided by 4, and we'll just leave it at that. G equals 23 over 4. We could simplify that to a mixed number, but we'll just leave it as an improper fraction. All right, looking at the next page here, a scale is a ratio between two sets of measurements, such as 1 inch and 5 miles. A scale drawing or scale model uses a scale to represent an object as smaller or larger than the actual object. A map is an example of a scale drawing. So here we are, example 5, what we talked about in our first page of this lesson. So scale drawings and scale models. On the map, the distance from Chicago to Evanston is 0.625 inches. What is the actual distance? So let's find Chicago here. And let's find Evanston, that is here. If you measure that on the actual map, it is 0.625 inches. So we know that we're going to have the map is to the actual distance here. So 1 inch is to 18 miles. And so what is it on the actual map? When we measure it on the map, we would get 6.25. So the actual distance is what's missing. So now we use cross products. 1 times x is going to be x. 8 times 0.625, that we see right here, is going to be 11.25. So the actual distance in real life is 11.25 miles. So the actual distance between North Chicago and Waukegan is 4 miles. So here is Chicago. And I guess they're talking about North Chicago. Oh, here, North Chicago up here. So North Chicago here and Waukegan right there above it. All right. So the actual distance in real life is 4 miles. What is the distance on the map? And round your answer to the nearest tenth. So we have the map to the actual miles. Again, as 1 inch is to 18 miles. So we'll set that up there. And then the actual distance in real life is 4 miles. Right. So we'll put in the 4 there. And the distance on the map is the unknown. So 1 times 4, multiplying our extremes, is 4. Now multiply our means. 18 times x is 18x. Divide both sides by 18, that we see right here. And that would leave us just x on the right. And 4 divided by 18 is approximately 0.2. So the distance on the map is about 0.2 of an inch. Here we have, whenever we're talking about scale, a scale written without units, such as 32 is to 1. Notice that there's no units on there. Unlike before, whenever we had the, I want to go back here. Do they give us the scale? Yeah, right here. Notice that the scale drawing on the map is 1 inch is to 18 miles. Well, the first value is in inches, whereas the second is in miles. But what if we have something like this where we just have 32 is to 1? Well, this means that there are 32 units of any measurement that correspond to 1 unit of that same measurement. And I've got some models here represented. For instance, look at this Deutsches Schnellboot German fast attack craft. So it's a German fast attack craft. And the scale we see underneath the logo, the company logo of Revell, we see 1 is to 72. That means that if you build the model and then measure the model, and the model is X number of inches long, you would multiply that times 72, and that would tell you how many inches in real life that ship is. So for every 1 inch of the model, in real life, there are 72 inches of the actual boat. Here we have another one, a nuclear carrier, the USS Enterprise. Now, an aircraft carrier is a pretty big boat. So 1 is to 720 is not very surprising. You might build these two models, the German fast attack craft and the aircraft carrier, and sitting on your table, both models might be pretty close to the same length, but in real life, this aircraft carrier is a heck of a lot longer than this German fast attack craft. So it doesn't surprise me that the scale is 1 to 720 compared to the German fast attack craft that's only 1 to 72. So you build a model, and for every inch of the model, in real life, there's 720 inches of the actual aircraft carrier. And then over here, oh, there it is down here in the corner, 1/25th scale right here. So the model of this car, once you build the model of the car, if you were to measure the car and it was a certain number of inches long, then you would multiply that times the 25, and that would tell you how many inches the car is in real life. So that's the difference between a scale without units and then like in our map where we have a scale with units, where there's units involved here. All right, at 32 minutes on this video, so I think I'm going to go ahead and call it quits at this one. We're going to kind of skip all this stuff here that might take us a little bit longer. All right, so that's everything I have for Chapter 2, Lesson 7 of Algebra 1, Rates, Ratios, and Proportions. Thank you.